In stats, we continued on with confidence intervals, and we looked at some of the properties behind it. So first off, here's our formula right here. And we need to remember that this portion right here is the margin of error. So maybe somewhere on this page, you want to define margin of error. Margin of error is the number of standard deviations times the standard deviation. And when I ran out of room there, when we add and subtract it, from the statistic, it will give a range of values that is likely to contain the true value. So write that somewhere on your paper, bottom of this page, top of this page, next to that. Margin of error in this handout, it changes. It depends on what we're calculating. But if we're talking about a 1 proportion z interval, it's z times the square root of p times its complement divided by n. And that's me. That's margin of error. All right? That's a whole equation all by itself. And we're adding and subtracting it from p hat to get our confidence interval. We didn't need that formula before. I don't know. Some people use the formula, but most people use the calculator. And they just write 1 prop z interval. So on that last handout, I told you could just write this. But something happens later on in this handout, and that is finding a sample size. It's very backwards. So we need to go off this formula that I just wrote down to answer this question. And one missing piece that is really hard to find, there's a few missing pieces, but one missing piece is z. How do you find z? And that is in table B. They printed it on the bottom row. So what they've done, we'll look at it in a second, is they've taken the bell curve. And if I'm doing a 95% confidence interval, that means I'm trying to find values that fall in this middle 95%. Because I think that those are the plausible ones, and this out here and this out right here are not plausible. Those are significantly far from the true value, right? We've talked about this before, and how 5% is our level of significance. So this is like backwards. This is saying 95% of these values represent a possible true value. It's a pretty clever way to approach this. So I need to find this, and I need to find this. If you know calculus, you can integrate and you can find the z values on the normal function. If you use the inverse normal function on your calculator, you can type in the area, and that'll give you z. But you have to be clever when you type it because we need the middle 95%. This area right here is 025. So if you type in 975, that'll give it to you. So if you type in that, you're going to get a z-score of 1.96. But let's just use the formula chart. Go to the formula chart, flip to table B. Oh, by the way, here's a very generic form of a confidence interval. This is the margin of error right here. And we're about to find the critical value. So if you keep on turning in your formula chart, your first table is table A. This is the bell curve right here. You could find it in here, but it's annoying to do that. Here's the positive side of the bell curve, positive z's. And then table B, this is the t distribution. We're going to talk about it this week when we move on to means. But it's very useful if you read it from the bottom up. You can read this two different directions. You can read it top down for hypothesis testing, or you can read it bottom up to work a confidence interval. Read from bottom. You might write this on your table B. For confidence interval critical values. And this infinity row is the z values. We're going to talk about why it is when we get to the t distribution, but for right now, just know, be confident, that's a bad joke, that those numbers I drew the arrow at are all z values. So when I do a 95% confidence interval, z is 1.96. Last week, when you did a 90% confidence interval, the calculator used 1.645. In a minute, at the bottom of our last page, it asked for a 99. That's 2576. So these three confidence levels are the most popular. They could ask any of these. If they're really evil, they won't ask one of these, and you'll have to do the inverse norm thing. But I bet they'll ask one of these, especially one of the circled ones. All right? So table B is very useful if you're doing a confidence interval. All right, let's go to the question. Skim through that real quick. Maybe hit pause. All right, this is a backwards problem. We are not constructing a confidence interval. We are finding a sample size so that a researcher can construct a confidence interval later. So this is a very backwards problem. It's like a planning problem. It's a very common problem. We need to find n. So if I know my formula for a one prop z interval is this, then all I care about is the plus or minus part. I care about that, and I'm going to leave alone that p hat on the left of that interval. So I know ME is z square root of p hat 1 minus p hat over n. And I need to fill in all the pieces and solve for n. All right? This is the margin of error. That's the boss saying, I need you to be, find this value within 3%. I need you to be that accurate. So I know on the left, I have 0.03. If I go to my formula chart, that 95% tells me Z is 1.96. N is my unknown, and I am totally stuck right now because nowhere in the paragraph does it tell us what p hat is, which makes sense because I haven't even taken a sample yet. How could I know what p hat is? If a possible p hat is not given, then use 0.5. So 0.5 is a worst case scenario. 0.5 allows for the most variable situation. It's not cheating. It's not being lazy. It's actually being conservative and accounting for the most error. Letting p hat equal 0.5 allows for the most variable circumstance. I think it dawned on me why we do that when I went back to geometry and I looked at 2D figures. If I'm looking at a quadrilateral, the figure that maximizes the space is a square. So if I'm multiplying two numbers here, if I want to maximize, create the worst possible scenario so that I meet my boss's condition of 3%, I need to account for that worst possible scenario. So if I let p hat equal 0.5, then I'll be guaranteed to meet his requirement. I'll be within 0.03. And we'll prove it on part B. So you let p hat be 0.5, and then you just have an algebra problem to solve. Unfortunately, I have run out of room, so I'm going to need to erase. So let's get rid of some of this writing, and let's solve this equation. I'm going to divide both sides by 1.96. And multiply 0.5 times 0.5, and I have this. I'm going to square both sides. I'm going to multiply both sides by n. And last step, I'm going to divide by that horrible fraction squared. You do not have to show this work. All you have to show is setting it up right here and the answer. When I type that in, I get 1067.1. Now think for a minute. If I round down to 1067, I'm going to risk not being within 3%. I need to bump it up because as n goes up, the margin of error will go down. So I need to round up. Just remember that. I need to round up 1067. 68. If I were you, I would write down the decimal answer as well to prove that you knew what you were doing. But to be honest, all you have to do is write the two things I circled. So you guys try part B. One little thing changes. Maybe hit pause and try your algebra. All right, part B is 0.03 still 1.96. Now p hat is 0.8, and I need to solve for n. You can use nsolve on the calculator. You can go all calculator if you want, but in the end, you're going to end up going 0.16 divided by that horrible fraction. If you want to see me do it, this is how I do it. I divide the margin of error by 1.96. Then I square it. Then I take p times its complement, and I divide by that tiny number. 682.95. At least 683. So all I grade, once again, are these two things. All right, we just proved something. As p hat moves away from 0.5, the needed sample size decreases. Look at the two answers. 1068 down to 683. P moved away from 0.5 on part B, moved to 0.8. Notice if p hat had been smaller, if it had, for example, been 0.2, the same thing would have happened. N decreases. The needed N decreases. All right, let's look at one more thing. This is a long video. So what if we change the confidence level? What if we change it to 99%? If we look at table B, Z is 2.576. I'm going to make a note here. Look at bottom row of table B. And that tells you 2.576. Then let's plug everything in. Still 0.3 for the margin of error. And back to 0.5 for p hat. Let's solve for n. If you type that in, you get 1843.3, so at least 1844. Try the last one without me. Hit pause and see if you get the same. 0.03, 2576. This time 0.8. You end up getting a decimal of 1179.7. So at least 1180. We just proved one more thing. All right, I hope that all made sense. Hopefully, I think the video jumped a little bit, but as as the confidence level increases, that's what I wrote at the very bottom of the screen, the needed sample size increases. So I think the video jumped a little bit, but hopefully that made sense. You're multiplying by a larger z value. See y'all later. Bye.